So take the solution. A moment. All right. So while talking about thermodynamics of ideal solutions, we have discussed that these four fundamental properties go through changes like this. For example, the change in the molar volume of components in an ideal solution, that doesn't change. Uh, the components pretty much remain the same as they were uh, before the solution. That means in this pure state, they were pretty much the same what they are after the mixing state. There is no creation of enthalpy. There is no change in enthalpy. Enthalpy stays the same, which tells you that uh, there's no reaction between the solution components. But the fact that this solution is, or when you mix two components, it immediately mixes, and that's driven by the fact that there is positive change in entropy. And you know that free energy is a combination, Gibbs energy is a combination of enthalpy and entropy change. And for the fact that there is positive entropy change, and when the term is made into a energy term, it becomes minus Ts. That becomes a total negative quantity, and there is no enthalpy change. So eventually, the Gibbs energy change becomes negative. Don't worry about the signs here, or be mindful about the signs. Del S, the change in entropy here, the formula comes with a negative sign here, but the fact that this term itself is negative, this makes this quantity positive. And on the contrary, the Gibbs energy change, the formula itself there's no negative number, but then the fact that this again is a negative number, this makes the whole thing negative because R and T are positive numbers. So even in ideal solution, in the absence of interactions between components, it still goes for spontaneous mixing, and that's typically driven by entropy change. All right. Now, when things are not ideal, when say there are a little bit of interactions between the components, that's where, in a way, you could say that it doesn't obey Raoult's law. Then it sort of, in the dilute solution regime, it follows a simple law which is called the Henry's law. In that situation, what could happen? Okay. Now, you know that the activity of the component in a solution and its mole fraction are one and the same quantity in case of Raoultian solutions, right? It's just simply AI is equal to Xi, or the numerical factor is 1. That is in the absence of interacting forces. But then when there is interacting forces available, it doesn't follow Raoult's law. That means AI is not Xi, or AI is slightly different from what the mole fraction is. Mole fraction, as you know, is based on numbers. You know, how many moles of one particular component is there in the total solution, and all the mole fractions put together would eventually give you 1. If it is a binary solution, A is equal to 1 minus XB. And likewise, if you have a ternary solution, you have XA plus XB plus XC is equal to 1. So all the mole fractions added together should give you 1. But then when it deviates from Raoultian behavior, which is called the non-Raoultian solutions, we connect these two terms, the activity and mole fraction, by a term called the thermodynamic activity coefficient. You know, we've seen that gamma is less than 1, then there is a negative deviation from Raoultian behavior. That deviation would be called a negative deviation from Raoultian behavior. And when gamma is more than 1, that's a positive deviation from Raoultian behavior. Negative deviation meaning that the activity would not be as high as the mole fraction. The activity will be slightly lower than the mole fraction. And on the contrary, here, when the positive deviation we're considering, then the activity will be slightly higher than what it is in the mole fraction. So these are the two terms that we can consider. And likewise, many solutions would actually fall into any of these categories depending on their interactions between the other constituents. And some of the examples here is that you could see the iron nickel solution diagram. That's probably at 1600 Kelvin, perhaps. Need to check, but probably it is 1600 Kelvin. And you could see that here this is iron 100% and nickel 0%. And this is nickel 100%, iron 0%, and anywhere in between is a combination of iron and nickel in the solution. And you can see that the mole fraction is given from 0 to 1 here in the line of the mole fraction of nickel increasing from left to right. Right, to talk about 0.4, that would be 0.4 nickel and 0.6 iron. Now, the activity here is normalized, and it's 1 for both things, so that all those things can be put on the same graph. And you see that the ideal Raoult's law kind of behavior would have been simply, these straight lines. Okay, and the combination would have been somewhere like this, or where if you look at the squares, the open circles here, these are experimental numbers given as activity with increasing nickel concentration, and you'd see that it's slightly deviating from the Raoult's law behavior, and it's sort of going through negative deviation in the sense that the activity is actually lower than what it would have been had it been based on Raoult's law, which is AI is equal to Xi. You see that this is 0.2, that's Xi, let's say I is nickel, then this should have been 0.2 here, okay, according to Raoult's law. But then you see that the experimental point is here. That means the activity of nickel is slightly lower than its mole fraction, which is given here. All right. So this is indicative of a negative deviation. Likewise, you could see that the concentration, the activity of iron is it should have been like this, but it's coming below here. This also gives you a negative deviation. All right. And the idea of Henry's law, that's why it is said that it is in dilute solution, because what we are trying to do here is that we're trying to put a formula to its behavior, and if it is a curve, you can't actually put a straight line unless you define a region, right? So we define the region that this is if we talk about in a dilute solution region, that means if iron is the major phase and nickel is the minor phase, that means we are kind of limited to this region. And in this region, the behavior of activity with increasing nickel concentration, it's shown by a curve which is like this, right, in this region. And this region can be approximated by a straight line, which is like this, which is kind of a tangential line, sort of matching or into a 4 point in the regime. Okay, so that's what is given as Henry's law. If you like to apply Henry's law here, then you probably won't be able to apply, because it's simply a proportionate factor. That's what is given in Henry's law. But that doesn't preclude, or that doesn't indicate that the behavior of a lower activity than mole fraction would not be applicable in higher concentrations. This is what would be seen throughout the composition regime. All right, but then how do we put it in a formula is what is given here in the dilute solution regime. And in the dilute solution regime, a Raoult's law can be modified, simple Raoult law can be modified into a simple numerically based Henry's law. Okay, it's simply a change in the proportionality constant. And this, since it is a simple straight line, it can only be applicable in the dilute solution regime. All right, so when we talk about Henry's law, it's in the dilute solution regime. Likewise, you could see that it's even smaller kind of behavior. You could see that the activity of iron or the activity of iron, which is in a dilute phase in the matrix or major phase of nickel, you could see only the straight line up to 10%, up to 10% of iron in nickel. And beyond that, it sort of kind of comes back. Okay, so Henry's law you won't be able to apply here. Although the region here would still be called negative deviation from Raoult's law. But then this area, you cannot approximate or apply Henry's law to be able to calculate the effective activity, activity of iron in nickel. So the negative deviation or positive deviations, these are across the binary solution composition, but then the applicability of Henry's law is going to be only in the dilute solution regime, because since it's simply a numerical factor. On the contrary, if you talk about Raoult's law, it's simple. You don't have to really worry about dilute solution or something, right? Because it's an ideal solution, and you can apply this all over the composition range. All right, and likewise, you can see an example of the iron copper diagram. I call this a Fenny diagram, and this is a Feku diagram. It's just a lighter note of sort of remembering things. And you'd see that here is a huge sort of enlarged or very accentuated positive deviation that can be seen in the iron copper system. And this is when talking about iron liquid and copper liquid, certainly at a higher temperature. And that's what the Raoult's law would have been like this. But then what you get experimental points is, the activity of copper is kind of showing a bow-like behavior, and it's very much higher than what it would have been had it been in a Raoultian solution. And almost the same reciprocating kind of behavior is seen by the activity of iron, which again goes here, okay, in this identical liquid. So the exaggerated positive deviation from Raoult's law is seen in the iron copper liquid solutions. And here also you could see that the concept of Henry's law can only be applied in the dilute solution regime, and beyond that the straight line doesn't follow. It actually bows down. Same way, same thing for activity of iron can only be seen only through a very small region, which is about 5% iron and copper. Here about also 5% copper and iron. Right. So these are the two examples, and you could actually find many such examples in the literature. Actually, it is difficult to find examples of Raoult's law, but it's kind of easy to find examples of solutions that could show either positive or negative deviation. Right. Okay. Now let's see if you'd like to get into the thermodynamics of non-Raoultian solutions, then the normal thing is to figure out what happens when temperature changes and how the solutions behave, right? And let's say if you look at the free energy of each component upon mixing, that you can write as RTL and I, RTL and AI, which is activity, and AI you can write in terms of gamma and Xi, because it's a non-Raoultian solution. So you can have to invoke the gamma here. Okay. Gamma I, which is a thermodynamic activity coefficient part. Right. Now, if we use the Gibbs-Helmholtz equation like we used for other solution, for the Raoultian solutions that we used, you'd see that del by del T of del G by T of a component upon mixing, this is the term, then you can write this equation is del H, the enthalpy change of the component upon mixing by T squared. This is the pretty generic formula. Depending on the type of G you use in the equation, you'd get the same type of enthalpy. Okay, the Gibbs-Helmholtz equation is just a formula to connect the free energy, Gibbs energy with enthalpy, right? The type of Gibbs energy that you use here, or the specific component, the nature of the reaction, Gibbs free energy that you use here, you will have to use the same enthalpy here to be able to apply Gibbs-Helmholtz equation. Now this we can write here as from here we can write RT ln AI, and that means ln xi ln gamma I. You can actually see that this can be written as the R ln gamma I, because xi is not a function of temperature. Right? So you can approximate these things as del by del T of R ln gamma I. So it's a functional relationship. It has the del G. It has a functional relationship with gamma I. Gamma I is a thermodynamic activity coefficient. Now, since you can't really sort of get an idea of a del G by T term, it's better to have it expressed in a directly measurable quantity, which is the enthalpy term. And we here can actually see the change of these with the change of this, or the change of this with the change of this. We can see the interrelationship of enthalpy and thermodynamic activity coefficient. Right? So we still further simplify this, you get that del R ln gamma I by del 1 by T, sort of makes a slightly simple. That is simply the enthalpy change upon mixing of that particular component. Right? Now from this relationship, we can actually see the kind of reactions that you could have, and what nature of solutions are there. We can sort of apply this principle. You mark this for a change of this, a temperature and the change of gamma, and this can be reflected here as the change in enthalpy. Okay, let's see. Okay, now now we are considering cases. Since if we have to broadly define the kind of non-Raoultian solutions you have, we sort of split it up into two, like we talked about. One is this quantity with gamma I becoming more than 1, or gamma I becoming less than 1. Okay, and how these solutions would behave with the change in temperature, and how is it related to the enthalpy. Turns out, increase in the temperature, no matter what kind of solution it is, okay, increase in the temperature makes the non-ideal solution to behave like an ideal solution. If you increase the temperature, the extent or the degree of non-ideality actually decreases. That has been seen by experimental methods. Okay, so you can simply write that increase in the temperature of a non-ideal solution decreases in the extent to which its components deviate from ideal behavior. That means if it is a higher positive deviation and you increase the temperature, then the positive deviation could be slightly lower. Likewise, if a non-Raoultian solution, a combination of components uh, in the mixture give negative deviation from Raoultian behavior, and then you increase to the temperature of the solution a little bit, you would see that the extent to which the negative deviation happens would be reduced. That's an experimental fact. Now, so yeah, the Henryan solution. Now, what could happen is that if gamma I is more than 1, right? That means the increase in the temperature, that is d gamma by dt is positive. D gamma by dt is positive. That decreases gamma I towards infinity, because that's what we know, because gamma I is equal to 1 is indicative of Raoultian behavior. So we can simply say that if gamma I is more than 1, if this kind of solution that we're talking is gamma I more than 1, that's positive deviation of Raoult's law. And in this system, if we increase the temperature, the gamma I would come towards unity. Okay, and that would see that the enthalpy of formation is positive. Okay, can we see that here? If you see that if increase in temperature, if talk about gamma I is more than 1, gamma I is more than 1, and increase temperature, gamma I is sort of reducing. Because from more than 1 it will come to less than 1. Right? And if you increase in the temperature, what is happening to this part? You're talking about 1 by T. Right? If you're increasing the temperature, this part is decreasing. If you increase the temperature, this part is also decreasing. The decreasing part by decreasing part is a positive quantity. So del H is going to be a positive quantity. And if del H is going to be a positive quantity, that is an endothermic reaction. Right? So that's what I'm talking about, is enthalpy of formation is positive. That means when the two components A and B mix, it's an endothermic mixing. Remember, we are talking about non-Raoultian solutions where, contrary to Raoultian solutions, ideal solutions, there is some amount of interaction, or the del H part is not absolutely zero. There has to be a part. It's an mixing. Right? Now, when there is an endothermic mixing, it indicates that the hetero-bond energy is less negative than the homo-bond energy. That means the AB type bond energy is less negative than the AA type bond energy or the BB type bond energy. That means the bonding within the components is much stronger. Like talk about the component A and the bond between the AA bonds are much stronger, it's more negative than the AB kind of bond. If you have two components in the mixer solution, you take A and B and there could be some interaction. That interaction energy is less negative than the interaction energy between A and A or B and B. So the similar type of bond energy is much stronger, much more negative than the dissimilar type of bond energy. Right? So that's what is indicative of positive deviation. That's what is indicative of this endothermic reaction. And in this situation, what happens is that A and B would not like to mix with each other. Okay, there is a tendency towards phase separation. All right, and clustering. They'll say A would like to be with A. Okay, B would like to be with B. Okay, so segregation and A and B to sort of separate out, and that's where new phases are formed. Right, so that's kind of an indication that if there's a positive deviation, these things don't like each other, and that they like to stay separate. Right, that's the nature of clustering. Now consider a case where there is uh, gamma I is less than 1. Gamma I is less than 1. Gamma I is less than 1, we normally identify that as the negative deviation from Raoult's law. Okay, and if you increase the temperature, then d gamma by dt becomes negative. Okay. So if you go back to this one, let's say if gamma is less than 1, and if you increase the temperature, that means you're decreasing 1 by T. All right. If you increase in temperature, this part is a positive. If you increase the, I'm sorry, if you're increasing temperature, 1 by T is decreasing, so there is a negative deviation here in the denominator part. And if you're increasing the temperature and gamma is less than 1, and we know that increase in the temperature leads the non-ideal behavior to ideal behavior. So this gamma is less than 1 and showing a negative deviation from Raoult's law. And with the increase in temperature, it will start showing positive, it will start showing less negative deviation. That means the gamma I, which is less than 1, would try to go close to 1. All right. In that sense, this is increasing. So this part is increasing and this part is decreasing. That means the ratio is always a decrease. That means if gamma is less than 1, this del H is an exothermic number, is the exothermic quantity. The enthalpy change is actually negative, and that is an exothermic kind of mixing. All right. So what does it mean in terms of the physical things that are happening? Is that the hetero bonds, the bonds between A and B, are more stronger. That means the AB bond strength is more negative than either A type bonds or B type bonds. That means the homo bonds, are less stronger than the hetero bonds, right? And if that is the situation, A would like to be with B, and B would like to be with A. So that what it will lead to is that if you're talking about a solution where A and B are there, and A likes B and B likes A, so it's uniform mixing, right? All A atoms would like to be surrounded by B atoms, and all B atoms would like to be surrounded by A atoms, and then how best they can be surrounded would depend on the composition. Right? When you have a 50-50% solution, then all will be equally surrounded by each other. The A will be surrounded by X number of B's, and B will be surrounded by X number of A's. That's what statistics says, but the availability of atoms say. Likewise, you can talk about 20% A and 80% B, and there'll be optimal distribution of A around A. That'll give. Okay, so that's where A and B completely sort of mix with each other, and that actually gives rise to new compounds. A certain combinations of A and B with different systems become amenable for a proper crystalline structure, which leads to the formation of newer phases in the phase diagram. Okay, I would suggest that you have a cursory look at iron nickel phase diagram and iron copper phase diagram, and look at where it is positive deviation between the compounds in the liquid state, and where is negative deviation from the compound in the liquid state. And because these solutions behave like that, look at how their typical phase diagram looks like. This is your sort of assignment. You can Google these phase diagrams. I should have put it here, but then you do some work. Okay, just Google these phase diagrams and see how iron nickel phase diagrams looks like, and how iron copper phase diagram looks like, and how these things are different based on the fact that one liquid gives a positive deviation and the other liquid mix gives negative deviation from Raoult's law. All right, so that's how you could see that these enthalpy or entropic quantities actually lead to certain behavior in phase formation and microstructure development. Right? Okay, so okay, I think we'll talk about regular solutions in the next class. That's going to be slightly longer. I think we'll keep it here today. Regular and sub-regular solutions we'll do in the next class, and kind of wrap it up. We'll not go any farther, because we can actually start from this ideal, non-ideal, regular solution, then take it to development of two-component at least phase diagrams. But then we don't have much time, right? That will be, maybe you can, the phase diagram course will take care of that. I think my job is to give you the basics on which you can understand phase diagrams in higher semesters, right? So I'm stopping the recording. If there are questions, we'll take and discuss in the next few minutes, right? Okay.